All right, hello everyone. I thought I'd make one final video on analytical chemistry, or the final in a trilogy of the three different analytical techniques you'll be using this year in terms of spectroscopy at least. There'll be some chromatography and volumetric analysis coming up. But we'll finish off having looked at NMR and IR with a look at mass spectroscopy. So as the name suggests, mass spectroscopy is going to be looking at mass. Hopefully you know this already. So we're just going to dive into having a look at some of the questions here. All right, so as usual, let's start with some multiple choice. Now there aren't a whole lot that are exclusively mass spectroscopy, and a lot of these questions I've kind of already covered in previous ones, but just completely skipped over the mass spectroscopy aspect of it because you can actually just answer the whole question using the hydrogen carbon NMRs and the IR spectrum. So let's have a look at some that you kind of need the mass spec to actually have a look at. I will refer to it as MS or mass spec because mass spectroscopy is a lot of syllables. So our first one here, we have an unknown organic compound that contains carbon, hydrogen, oxygen. We know that there's no carbon-to-carbon double bonds. There's a molecular ion peak. So remember that the molecular ion is going to be the parent ion, i.e. the biggest ion. The ion that, or the formula that is what the original molecule was, without having any bonds broken or anything like that. All right, and it's found at a mass to charge ratio of 74. So it had a mass 74. And then we find a small peak in the mass spectrum at a mass of 75. So how does that work? If the mass of the compound is 74, how do we get 75? If the only thing you can do is break up? Well, there are basically three possibilities here, and they're all the same thing. So basically, we have some form of an isotope is present. So we've got three elements here. We've got carbon, hydrogen, oxygen. Either we've got a deuterium, we've got some kind of carbon 13 or 14 or something like that, or, well, it can't be 14 because then it would be 76, or we've got oxygen 17. One of the first two being the more likely there. So we've got some kind of form of isotope there that's a bit heavier, which is why there's a little peak. It doesn't say a big peak, it does say a small peak, because a small fraction of hydrogen and carbon have an extra neutron. So if any one of the hydrogens or carbons in the molecule has that extra neutron, the whole molecule will weigh one more and give us that extra mass. All right, next we've got an unidentified organic substance with the molecular formula as shown is found to react with a base. This is why it's important to read the question. This is critical to answering the question. An organic thing that reacts with a base. At this point in your organic chemistry journey, the only possible scenario is that it's a carboxylic acid. So basically it's this, and then there's something going on over here. Basically it has to be a carbon there, and something's going on a bit further down. All right, it has a mass to charge ratio of 88, which isn't particularly useful because we already know the formula. Which one of the following species is consistent with a peak of the mass spectrum at m/z equals 45? All right, so if you see the mass here, you can kind of have a look at it and see what matches up with the mass here. Which of these fragments weigh 45? I did the mass before, but we can go, so the top one we can go 12 plus 32 plus 1 is 45. Okay, that makes sense. Next one we can go 24 for 2 carbons plus 5 from the 5 hydrogens plus 16 from the oxygen is going to equal 45 as well. This one here is 46. If we add them all up, it's just the one above it plus 1. So this one's out of the question. And the one below is really, really big. That's just the molecular ion peak. So that one would just be 88. So that's out of the question. So the only two that are in competition are these two. And the question you have to ask yourself is there any way that we can break a single bond and make this fragment? Is there some way that we can break a single bond and make this coup fragment? Yes, there is. We can break a single bond there, and the electron goes this way, that becomes a radical, and we get a positive ion here that weighs 45. That makes sense. is there any way we can break a single bond and get the CH3CH2O? No, there's no way that that's going to happen because this oxygen, there's no double bond here anyway. This one's not attached to anything. And this one over here, there's no carbons on the end. If there was an ester, you could perhaps have, and there was CH2, CH3, this could potentially fall off, which is why it's important to read that it's a base so that you know it's a carboxylic acid and not an ester. So because of that, we know that the answer is A. We can break this bond to make the top one, but there's nothing to make B. All right, the mass spectrum of alkanol T is provided below. Remember, an alkanol is just an alcohol that only is an alkane with the OH tacked onto it. What is alkanol T? So first thing we should be looking at when we're looking at a mass spectrum is what's the molecular ion, what's the parent ion. So we're looking at around 60 there. So 60 M/Z, we'll see what matches up. So butyl 1-ol is going to be C4H9OH. So it's going to be 48 plus 10 plus 16. So 58, 64, 74. That is way above 60. That is out of the question. Ethanol, you might just already know this one already, but if we add up ethanol, it's 46. That's out of the question. Methanol is even smaller than ethanol, out of the question. Propane 1-ol ends up being C3H7OH. So 36, 43, 59, 60. Propane 1-ol is looking pretty good as our answer for this one. So a lot of the questions for mass spec, we can kind of use a process of trial and error just to answer them, figure out what the things are. Here we've got a chemical, contains carbon, nitrogen, hydrogen in the ratio 4:1:11. We've got the IR spectrum. The IR spectrum is showing an NH stretch. So see how it's weak. And if there's kind of these fangs, then that's a kind of a giveaway that you've got an NH there. And it doesn't really look like there's a C double bond O or anything like that. Of course, we've got just a carbon hydrogen stretch here, which isn't particularly useful. So we know it's some kind of amine. We've got the mass spectrum. Now, remember, first thing we're going to look at is the parent ion. It's at 73. So what is the molecular formula for the parent molecule? Just for your answer using information from the mass spectrum. So to find the molecular formula, we need to take the empirical formula and then compare it to what we know the mass is. Divide one by the other. So the empirical formula is C4N1H11. I'll put the H in the front because it's not a convention to do it that way. So the mass of this, or the molar mass of this, I should say, is equal to 48 plus 11 plus 14, which, what do you know, ends up being 73 mass units. So I would say something like the mass of the, or the molar mass of the empirical formula equals the molar mass of the parent peak at 73 M/Z, and therefore the empirical is the molecular formula, something like that. So we just basically you just needed to say it's the parent ion. You look at the molecular ion peak here. You say, okay, so the mass of it's 73. Well, that's just one lot of 4 of carbons, 1 nitrogen, and 1 lot of 11 hydrogens. So you get your 73 then. So we're looking at C4H11N. Identify the fragment that produces the base peak. So remember, the base peak is going to be the tallest one. So we're looking for something that weighs 30. So I'll start to draw out some potential structures. If we do part 3, it'll actually make the previous part easier, in my opinion. We know we have NH stretches, and we're not going to be dealing with secondary amines in year 12. So it's going to look something like this. And then there's kind of a few things we can do. I'm going to draw the potential ones here. Now, for here we draw structural formula, so I should put the hydrogens on. I'm going to be lazy and not do it, but you should probably do that. So we can get that one. Or we can get this one. So basically we can branch at the first carbon or the second carbon. So 3 different molecules there. Which one, can we break a single bond in one of them that will make 30? If we break a single bond here for the ethyl, we'll get 29, which is close, but not quite there. And basically any of the ones we break here, so we can break off a methyl, will be 15. You're not going to get, you can't add 2 methyls together to get 30 or something like that. If we knocked off a whole propyl group here, then that would be, what's that, 43? So definitely not 30. So we're going to have to go at the other end. So we've got 16 from the nitrogen, 12 from the carbon, and 2 from the hydrogens here. So if we broke the single bond here, we would get a fragment that looked like that, and it would be 30, show up as 30 M over Z. So I'm going to do that there, CH2, NH2. Now, whenever you write a fragment, put the square brackets around it and put a plus on it, just to show that there's a positive charge on it somewhere, but we don't know exactly where the positive charge is. And we've actually drawn 3 possible structural isomers. All right, now we get the carbon NMR spectrum of the chemical that's shown above. So we've got the chemical shifts here. So we can go and look those up if we want. And give them a look up. And 20 is probably something like either a CH3 or a CH2. It's kind of a bit hard for that. And for the 50, probably looking at CH3, that would be the very lower bounds of the CH2, which is unlikely if there's a nitrogen nearby. And if there's 50, it's probably the one that's next to the amine. That kind of makes sense because we're expecting the one that's the lowest to be the one down the end. We're expecting the one down this end to be the lowest, and we're expecting the one closest to the electronegative element to be the highest. So that one there. All right. And then draw the skeletal formula for the chemical. Note the previous one said structural, this one says skeletal, which is consistent with the IR spectrum, the mass spectrum, and the carbon, the 13 carbon mass spectrum. So we can look at the shifts here to note that. What I will point out straight away is you should be able to look at this and go, oh, okay, there's 3 carbon environments. So if there's 3 carbon environments, we can look at this. We can go, okay, on this one here, we have 1, 2, 3, 4 carbon environments. Okay, so it can't be that one. This one here, we've got 1, 2, 3, 4 carbon environments. Can't be that one. This one here, we've got 1, 2, 3, and these are in the same environment because they're just branching off at the end there. These are different branches. One's a methyl, one's an ethyl. These are both methyl groups branching off here. So this is the correct formula. So we just need to write that in as a skeletal formula. So, oops, probably, actually, that's fine to put there. And then remember it is skeletal. So we're going to draw it like that. Carbon's gone. Don't put the hydrogens on the carbons. Instead put the hydrogens on the nitrogen there. All right. Another one. A bottle containing an unknown organic compound was examined in a university lab. There's an incomplete label on the bottle again. Man, these chemists don't know how to label anything. What uni is this? Anyway, so the empirical formula is CH4, and why you would write an empirical formula on anything, I don't know. So chemists hypothesized that the unknown compound was 1,2-ethane diamine, and then there you go. As spectrometry produced the following spectral data. On the diagram above, circle the base peak. The base peak is the tallest one. There you go, there's a mark. At what M/Z ratio is the principal peak that supports the chemist's hypothesis that the unknown compound has the formula of that? I would go ahead and say the parent ion or the molecular ion peak here would give you the best justification, because this is 60. That tells you the overall mass of the compound. Mass of this happens to be 14 plus 16 plus 16. Oops. Other way around. Doesn't really matter. 14 from this carbon, 16 from the nitrogen, 16 from the nitrogen, 14 from the carbon. And then it happens to be 60. So these are equal. So therefore, it suggests that at least, so that is the molecular formula. Even if we're not, we haven't really discussed what structure it could be. That's the only other potential structure you could have is 1,1-ethane diamine. So that would be the principal peak. You could do some other arguing after that about the fact that 30 would definitely suggest that it's this one rather than the other one, because you can just split it in half and it goes 30-30. That's why there's so many of them and so little of anything else. But this is the only one we need to discuss for this question. All right, write the semi-structural formula of the species that produces the peak at 30 M/Z. Okay, so exactly what I just said. So we've got, basically, we take compound here. We can say that NH2 is 16, CH2 is 14, 16 plus 14 is 30. And we can just split it down the middle, and then each one of these will weigh 30. So we're going to write that down. Is that the same fragment we had before? Make sure there's square brackets around it, put a positive charge on it, and we get another mark from that. So if you are unsure about the weight of a fragment or something like that, you can always just go through and cut different bonds and see what happens. If you cut the first one off at 16, okay, it's not high enough, we'll do another one. Cut it off again, okay, so that one's good. If you cut it off and you go too high, then try starting from another end. And normally one of those should work. All right, the mass spectrum shown above for a molecule with the molecular formula of this. What species is responsible for the base peak? Again, base peak is going to be the tallest one here. It's a 50, 51, 52, 53, 54, 55. So 55 M/Z. All right, so we've got a bunch of different formulas here. Which ones of them actually add up to 55? So I'm just going to look at the bottom. That's 55. So that's one's fine so far. C3H5, that's 36 plus 5, 41. Definitely not that one. C3, 36, H brings up to 40, plus chlorine is 75. So definitely not that one. And the top one is just the molecular ion. So that's definitely not going to be the base peak. As in, because the molecular ion's up here, so it's obviously not here. You can have the molecular ion peak also be the base peak if you have a really stable molecule and it just won't break apart. But that's not necessarily always the case, and it's not necessarily always not the case as well. So D is our correct answer here. And that's it. So there's a bit less mass spec compared to the other things. Give you guys some extra practice ones to do as well. But basically everything from here, you should be able to combine all of the different things that you've learned and take all of the spectral data to be able to identify a molecule. A lot of the time, the questions don't even require you to identify the whole molecule. So it's up to you whether you want to identify the molecule and then just go back and answer all the questions, or just try and go through it as fast as possible, whichever one works for you. But other than that, thanks for watching, and I'll see you guys later.